This video is to give you a brief introduction into periodic trends, where periodic trends come from, as well as the atomic radius trend. So go ahead and open up your foldable, and we're going to talk about trends in general first. If we were talking about something trending on Twitter or trending on YouTube, and we could take a zoomed out look at the entire world and all the devices that were tuning into those things, we would see this really great pattern emerging. And specifically trending on social media, we know that it's popular. So we're going to see this pattern of popularity. Trends in general are patterns. And instead of looking at what's trending on Twitter, how much better, we are going to look at trends or patterns in the periodic table. So these patterns in the periodic table, they come from one of two places. One, they come from electron configuration. Specifically with this electron configuration, we're talking about the Aufbau principle, building up. The other place trends come from, and this is probably new, it's Coulombic attraction. Coulombic attraction, all that is how positive and negative charges interact with each other. So you guys already know how positive and negative charges interact with each other. You guys know that if you have a positive charge and a negative charge next to each other, they're going to attract, like a north and south pole of a magnet. You guys also know if you put two north ends of a magnet together, two positive ends, they're going to repel. Or if you have two negative, they repel too. So it's really important that you guys keep in mind electron configuration and Coulombic attraction when we're talking about these trends. The first trend we're going to talk about is atomic radius. Now you guys already know what a radius is from math class. It's from our center of the circle out to the side, and we call that R, our radius. Well, let's see what that looks like in an atom though. So instead of the center of our circle, now we're looking at the center of an atom. The center of the atom is the nucleus, and our outermost edge, instead of a line of a circle, our outer edge are valence electrons. So we're examining the distance between that nucleus and those very, very outer electrons. Atomic radius, the distance from the nucleus to the valence electrons. For each of the patterns that we're going to examine, each of the trends that we're going to examine, we need to examine two things on the periodic table. We need to examine what's happening in a group, so up and down a column, and then we also need to look at what's happening across a period, across a row. We're going to start for atomic radius. We're actually going to start with a group. For the group, let's take a little sampling of things from group one. Let's start with hydrogen, then lithium, and then we're going to look at sodium. Okay, we're looking at valence electrons. Hydrogen's valence electron is in a 1s, lithium's in a 2s, and sodium's valence is in a 3s. So right there we've got valence. If we were to draw a picture of those atoms, here's my X, Y, and Z axes. If I'm looking at hydrogen, we've got our little 1s sphere in the middle. It's the first energy level, it's pretty small. And then we go up to lithium with a 2s, and this one's larger. It's going around the 1s. We can already see that the radius would be getting larger. Then if we kept going to sodium, and that's 3s, that's even larger still. So that's even encapsulating that one. And we can see every time that our radius is growing. So as a trend, as we're going down the group, it's getting larger, whereas it's smaller at the top. And that's pretty intuitive, but let's make ourselves a note. So as we go down, it's large down here, and it's small up here because we're adding another shell every time. Our electron configuration is growing. We have more and more energy levels. Let's talk next about what's happening as we go across a row, across a period. Let's just pick out a few things from our second period here as a sample. So we've got period. Let's pick out a couple things from the second. Let's go lithium, and we're going to skip a few and go to neon. We know that we're looking overall at our distance from the nucleus to the valence electron. So I'm going to put the valence electrons around here. Lithium has 1 because it's in the first group, and neon has 8 because it's in group 18. For this one going across a period, we need to talk about Coulombic attraction for this one. Inside lithium is an atom. We have a nucleus. Neon also has a nucleus. There's an attraction between the nucleus and the electrons going around. Our nucleus is a positive charge from all those positive protons. Electrons have a negative charge, so we see an attraction here between our nucleus and our electron. Lithium only has one valence electron, so in terms of attraction, just that one. Neon, on the other hand, has 8 valence electrons that are all attracted into the nucleus. This nucleus is a really big pull because there's so many more electrons here than there are here. Because of that, what we see happening is that neon is actually smaller than lithium. So we see that this is larger and this is smaller, and that's just because neon, there's more pull into the center. So that distance around it really is shrinking down and getting smaller there. Let's write that. I know we just wrote it above it, but I'm going to rewrite it a little bit neater. So I'm going to put across the top here, representing our period trend. It's large on the left side and it's small on the right side. Okay, now let's talk about what's happening overall in our periodic table. That way I don't just have to always examine a group or row. I can look overall. We see that it's small right up here, and then the large diverges down, which means we're going to have an overall arrow that starts at helium and it's going to go down to francium like this. And that's our atomic radius trend. That is the arrow, that last arrow that you really, really need to know. It's large here and it's small here, which means our largest element is francium. That has the largest radius, and helium has the smallest radius. In case you've ever heard me call francium Big Fat Frank, this is why. Because francium has the largest radius. It's the largest element. You guys need to be able to look at a periodic table and figure out where the elements are in terms of their size. So let's say you had chlorine and phosphorus. You should be able to look and tell, oh, phosphorus is larger because it's closer to francium. Okay, how about zinc and rubidium? Which one's larger? Rubidium is going to be larger because it's closer to francium. Or on the flip, if we said which one's smaller and we said sulfur or silicon, you would say, well, sulfur's smaller, it's closer to helium. To recap, you guys now know patterns in the periodic table come from 2 places: electron configuration and Coulombic attraction. Atomic radius is the distance from the nucleus way out through all that space to the electrons, specifically valence electrons. As we look at our groups and we go down, we are going to increase energy levels, increasing size. The left side of our periodic table on a period is larger than the right side due to our electron and nucleus attraction. Overall, francium is the largest element, helium is the smallest.